Okay, so welcome to the second lecture on indirect detection. So last time we talked about some simple estimates for indirect detection, and Neil kindly gave us a review of the thermal relic scenario this morning. So basically the two things that I want you to remember from last time are that in the thermal freeze-out scenario, we achieve the right relic density. We achieve the right relic density for a cross-section of order this for two-body annihilation. So this suggests that for thermal dark matter, we want to look at a mass scale below about 100 TeV. Now, last time I also wrote down expressions for general N for if you have three-body and four-body annihilation. I think Neil is going to talk a bit in the future about models where those processes dominate. But pretty generically, if this two-body annihilation process is present, it will dominate over three- and four-body annihilations simply because it has fewer powers of the dark matter density present. And if we're talking about a cold relic, after freeze out, the dark matter density has been Boltzmann suppressed. If we were to have something purely dominated by where freeze-out was dominated by three-body or four-body annihilation, we'd prefer a smaller mass scale, below about the GeV scale for three-body, and below about the MeV scale for four-body. But if two-body annihilation is present, it usually dominates. So for the rest of this lecture, I'm going to, when I talk about thermal dark matter, I'm going to assume that we're working in a regime where the two-body annihilation is the leading annihilation process. Although I'll just mention that some of the constraints I show are constraints at late time. At late time, the density tends to be even lower than it is during freeze-out. So if you do have models where three-body or four-body annihilation dominates freeze-out, they'll also evade a lot of the other late time constraints I'm going to talk about. Okay, the one other thing I want you to remember from last time was just the estimate that we did that for sort of GeV to TeV dark matter, we might hope to probe with indirect detection signals at the level of between 1 in a billion to 1 in a trillion dark matter particles, producing visible standard model particles over the edge of the universe. This was a very coarse constraint, just based on looking at how many dark matter particles will we have in the Virgo cluster, how many photons could we potentially see from the Virgo cluster if they were produced by a process like this. But I'll show you constraints next time which actually make it clearer that we can set limits on dark matter decay that correspond to lifetimes about 10 orders of magnitude longer than the age of the universe. That's equivalent to saying that 1 in every 10 to the 10 dark matter particles has decayed away over the age of the universe. Okay. So what I want to do first here is say, okay, if this is not the only way you could get the right dark matter relic density, but if you do have this dark matter relic density, what are the implications? So I'm going to focus in on this case where there is this annihilation process. It's a two-body annihilation process. And I want to look at what that implies. Well, okay, first, let me just say we can do a somewhat more. This answer is off by about a factor of 5, I think. So let's just use the actual more correct value, which you'll see in the literature in a lot of places. If you do this estimate more carefully, putting in all the order 1 factors, there's a paper by Gary Steigman to which I can give you the reference if you want to know, but basically we find that sigma v is 2 to 3 times 10 to the minus 26 centimeters cubed per second, which is about 2 times 10 to the minus 9 inverse GeV cubed. So when people talk about the thermal relic cross-section in the literature, this number is usually what they mean. There's a slight mass dependence in here, basically because of different masses the universe has a different number of degrees of freedom in the radiation field at the time of freeze out. As we expected from the simple calculation, this result is pretty close to being independent of mass. So first question we might ask is, okay, suppose we look at that simple analysis that we did for Virgo. Now we've got an estimate for a dark matter annihilation rate. Would something like this be visible from a galaxy cluster today, from a pretty close, big galaxy cluster? Well, for that, so we want to know what fraction of the dark matter particles in something like Virgo have annihilated away over the edge of the universe. If we produce standard model particles, we can just use this estimate that we had here. So for annihilation, it's no longer true that we just have some decay rate, but we have an effective decay rate, which is just n, the number density of the dark matter, times the cross-section. This tells us about the time scale for a dark matter particle to annihilate. It's dependent on the local density of the dark matter. So we always know the mass density of, if we know anything about dark matter, we know its mass density, not its number density. So if we've expressed a result like, okay, what fraction of dark matter particles, so a question we have is, like, for the thermal relic cross-section in Virgo, are we way above this number? Are we way below this number? That'll tell us roughly how observable this is. Now, Virgo, now n, this density of dark matter is not going to be constant throughout Virgo. It's going to be different in galaxies than it is outside galaxies. But just to get a very, very rough order of magnitude estimate, let's say, okay, suppose we're looking at a region where the dark matter density was comparable to what it is in our local neighborhood. Okay, so this is all, again, just rough estimates, just to get some intuition. So our local DM density is currently estimated to be about 0.3 to 0.4 GeV per cubic centimeter. So that tells me that if I take this thermal relic cross-section and I ask, okay, in our local neighborhood, what fraction of dark matter particles are disappearing, like decaying but through annihilation, then this gives us, so if we put in rho GM of 0.3 GeV per cubic centimeter, put in this of 3 times 10 to the minus 26 cubic centimeter, then this gives us basically 10 to the minus 26 per second divided by the dark matter mass per GeV. So this should look pretty familiar to you. This rate of 10 to the minus 26 per second, this is a similar rate of production of standard model particles as you would have from a decaying particle, with a lifetime of 10 to the 26 seconds, which is what we said we should constrain. So you would guess here that for GeV dark matter, this annihilation rate would be about as detectable as a decay rate of 10 to the minus 26 per second. For a TeV dark matter particle, you'd guess this would be like a decay rate of about 10 to the minus 29 per second. And those are right about the level of observability that we saw in Virgo. So two things I want you to take away from this. One, this thermal cross-section is, fortunately for us, this is one of the reasons that people like WIMPs so much. The cross-section that is predicted, that we should see here, is actually very comparable to the cross-section that you would need to get to see observable numbers of particles produced by annihilation, coming from our local galactic halo and coming from other astrophysical objects. The other thing that I want you to take away from this is telling us again that for annihilation, or for the decay rates that we can constrain, we're talking about, well, now for annihilation, we're talking about dark matter particles interacting with each other at a rate of 1 in, say, 10 to the minus 10 over the whole age of the universe. Okay? So if we ask, let's look at the dark matter particles in our local neighborhood, how many of them have ever annihilated? The number is extremely small. It's like 10 to the minus 10. So Neil talked a bit earlier about self-interaction between dark matter particles and the constraints on that self-interaction, and said that the rate needs to be the sigma of the cross-section divided by the dark matter mass. Needed to be at the level of, I don't remember what units he put in, but it's about 0.1 to 1 centimeters squared per gram. Those cross-sections correspond to 2 dark matter particles, to, on average, every dark matter particle scattering once in the lifetime of the object. These cross-sections correspond to 1 dark matter particle in 10 billion scattering over the lifetime of the object. Okay? So the cross-sections that we talk about for annihilation here are very, very small compared to the cross-sections that you would need for meaningful self-interaction or for significant depletion of the dark matter abundance in our halo. So it's back to what Neil said. These are weak scale this is a weak scale cross-section. What you need to get significant self-interaction bounds is strongly interacting dark matter. Yeah?
2 short questions. First of all, for the sigma V, we assume that couplings are order 1.
So this value of sigma V doesn't assume anything about the couplings. This value of sigma V is just this part. Is basically just this part of the equation. Okay, so we didn't have to assume anything about where this cross-section comes from. This is just saying, okay, the cross-section keeps the dark matter coupled to the standard model for a certain amount of time, and then when that rate becomes small compared to a Hubble time, the dark matter density freezes out. So you don't need to say anything about where that annihilation rate comes from in terms of particle physics. You can describe it purely in terms of the Planck mass and the amount of dark matter in our universe, which is parameterized by the temperature at matter radiation equality. Okay? Now, if you then go and say, okay, I want to associate a mass scale with this, then that tells you that you probably want a mass scale below about 100 TeV, and if you have a weak scale coupling, then you'll also have a roughly weak scale mass. But this statement about the thermal relic cross-section actually assumes nothing about the particle physics. It's just derived from the cosmology.
And second short question, where do we get the local dark matter density values from?
Good. So the local dark matter density value I am just telling to you. But so you remember how on the first day Neil talked about rotation curves, measurements of how fast particles are orbiting around the galaxy, and so that gives you a measure of how the total mass enclosed in a region varies function time. So you can do methods that are like that, somewhat more sophisticated, but basically measuring the kinematics of objects in our galaxy to try to infer how much mass you have in each region. Now, the easiest way to do this is basically to say, okay, one way to do this is basically say, okay, I have some model for where the baryonic matter is, I have some model for where the dark matter is with some adjustable parameters, and then I'm going to fit these parameters to my observed kinematic data. If you do this, so you can do this and you can get numbers like this, but at our local solar radius, I think the dark matter density is fairly comparable to the baryonic density. As you go towards closer to the center of the galaxy, the baryonic density rapidly becomes much larger than the dark matter density. And so it's much harder to directly measure the dark matter density in here. But people do things like they look at the motion of stars moving in and out of the baryonic disk to try to work out, to try to measure the surface mass density that way. If you try to look at like a non-parametric measurement of the local dark matter density, one that doesn't assume some model and extrapolate out from larger radii, then the error bars on this number are reasonably large, but we're fairly sure that at the location of the sun, at that distance from the galactic center, there is dark matter. Once you get in within about 5 kiloparsecs from the galactic center, so we're at 8.5 kiloparsecs, once you get within a few kiloparsecs of the galactic center, the error bars overlap with 0. So we actually don't have any direct kinematic evidence that there is dark matter in there. We just think there is because we know how particles gravitate. But yeah, so that's it's an estimate from kinematics. Great, thank you. Yep.
Shouldn't that be a rho squared if doing annihilation?
Good. Yeah. No, good. This is important because there are two different kinds of rates here. There's a rate where I ask, what is the number of annihilations per unit volume per unit time? Okay? That would have a rho squared in it. What I'm asking about here is, given some dark matter particle, what is the rate for this dark matter particle to annihilate away? Like, what is the probability that this dark matter particle annihilates away during some time? So then the probability for that dark matter particle to annihilate away during some time just goes like a single power of the dark matter mass. Similarly, for decay, the probability for a given dark matter particle to decay away in a given time just goes like 1 over the lifetime. But if I ask within a certain volume how many dark matter decays happen, then that will scale with the total number of dark matter particles in that volume. Okay? But no, that's good. That's a good question. That's an important distinction. Okay. So we know this is promising. This thermal Relic cross-section will give us a potentially detectable signal in the present day for weak scale WIMPs. It's not going to strongly modify the structure of dark matter halos because the rate is just pretty small. But we could potentially see it in indirect detection. What about earlier in the universe? Earlier in the universe, the dark matter density can be much higher than it is in the local halo. So we might ask just, okay, what if we did have something like this thermal scenario, what implications would that have? Again, this thermal scenario doesn't have to be the right answer, but it's an illustrative framework for just seeing what kind of effects you could have from dark matter annihilation or decay. Okay, so how does the dark matter annihilation rate scale with time? Well, we know that the number density after freeze out we know that if A is the scale factor, then the number density of dark matter scales roughly as a to the minus 3. Okay? Oh, sorry, does scale as a to the minus 3 unless there's something else that is producing or depleting more dark matter. Okay? So that tells us, so now I'm going to look at the other kind of annihilation rate, which is just the annihilations inside in a co-moving volume in a Hubble time. So here I'm going to take the annihilation rate, I'm going to multiply by the physical volume corresponding to a given co-moving volume, and I'm going to multiply and I'm going to multiply by the Hubble time. And this will give me some sense of how the rate of annihilations and how the power injected by these annihilations corresponds to just the number of, the number of baryons, the number of hydrogen atoms. We'll see in a moment why that is a useful diagnostic. Okay, so the annihilations per physical volume per unit time goes like n squared sigma v divided by 2. The physical volume, so this is number of annihilations per physical volume per physical time. The physical volume corresponding to a given co-moving volume is growing as the universe expands. So this will give us a factor of a cubed here, proportional to. So, and a Hubble time is h to the minus 1. So we know that n goes to a to the minus 3. So this is going to give us, a to the minus 6. So this is going to give us something that overall this rate scales like this. Now, I'd like to know how this A evolves with respect to time, how these A and H are related to each other. So during radiation domination, so there are two major epochs in the early universe. So during radiation domination, from the Friedmann equation, we know that h squared is proportional to rho, which means it scales like a to the minus 4. So that tells us h proportional to a to the minus 2. Whereas during matter domination, h squared is again proportional to the density, but now that's proportional to a to the minus 3 because matter is dominating the energy density. So this tells us that h is proportional to a to the minus 1.5. So plugging that into this result, what do I call this? I'll call this capital A, this quantity. Okay, this is the definition. That is not standard notation, it's just, I don't think there is a standard notation for this quantity, so I'm going to call it capital A for the moment. So that tells us that in radiation domination, this annihilation rate, this total amount of annihilation in a co-moving volume per Hubble time scales like a to the minus 1 if sigma v is constant with respect to a, and in matter domination it scales as a to the minus 1.5. So the number of annihilations and the power injected by annihilations in a co-moving volume per Hubble time decreases as we go forward in time, just as 1 over a throughout the radiation dominated epoch, and then somewhat faster once you enter the matter dominated epoch. So furthermore, in addition to this, we know that at freeze out, by definition, a dark matter particle annihilates roughly once. For each given dark matter particle, the average time for annihilation is roughly a Hubble time. So if we look at this annihilations in a co-moving volume per Hubble, so in other words, an order 1 fraction of the dark matter annihilates in a Hubble time. So another way, right, so when we describe A, so this is annihilations per co-moving volume per Hubble time, the number of dark matter particles per co-moving volume is a constant after freeze out. The co-moving density is conserved. So another way to say this is that this is directly proportional to the number of dark matter annihilations per dark matter particle per Hubble time. So A describes the fraction of DM particles annihilating per Hubble time. Okay, so now that we know this scaling, and we know that at freeze out this fraction is roughly 1, we can figure out quickly at any subsequent time roughly what fraction of dark matter is annihilating away within a Hubble time. So you learned about various important epochs in the history of our universe back in the cosmology class last week. So for example, let's consider BBN. So at BBN, the temperature of the universe is somewhere in the neighborhood of an MeV. We're still in the radiation dominated epoch. Let's suppose here that we have 100 GeV thermorelic dark matter, okay? We brought it just as an example. Now, I told you last time neither Neil and I have derived this, but it is generally true, and I can show you the derivation later if you're interested, that freeze out, we approximated the freeze out happens at MDM over T So we approximated that this happened at when this ratio was roughly equal to 1. Actually, for WIMPs, the ratio is usually more like 20 to 30. Do I have that the right way around? Yep, that's right. T is smaller than MDM by a factor of 20 to 30. So freeze out for this candidate would have happened at temperature of about 5 GeV. So this tells us, so the fraction of dark matter particles annihilating per Hubble time during the radiation-dominated epoch scales like a to the minus 1, which means approximately, ignoring changes in the relativistic degrees of freedom, it scales roughly as t to the minus 1. So at BBN, we expect roughly 1 over 5,000 DM particles to annihilate per Hubble time. What does it mean if roughly 1 in 5,000 dark matter particles annihilate? Well, so that means that in a Hubble time, 1 part in 5,000 of the total energy in the dark matter has been liberated. Okay, turned into something that might have observable effects. If it's turned into standard model particles, if it's turned into electromagnetically interacting standard model particles, then those particles could potentially affect nucleosynthesis. Now the total dark matter density is about 5 times the density in baryons, so 1 part in 5,000 of the dark matter density corresponds as about 10 to the minus 3 of the total matter density in baryons. Another way to say that, so a proton weighs about a GeV. So this is saying the thermal dark matter would, at BBN, be expected to inject an order of 1 MeV of energy per hydrogen atom, or per proton, or neutron. I have a dramatic backdrop to these statements, I guess. So yes, not sure that statement quite, yes. All right, so I have this dramatic backdrop, i.e. roughly 1 MeV of energy per proton. So this is in the same order as the neutron-proton mass difference. So if you take all this energy and can efficiently convert it into photons around this energy scale, you would guess from this that this could actually potentially have a fairly large impact on nucleosynthesis. I mean, this is an order 1 change to how much kinetic energy these particles would have traveling around, if you can take the energy of dark matter annihilation and convert it into changes on BBN. And so indeed, we can get and indeed, we do get constraints on energy injection from thermal dark matter. There are some subtleties here, because it's possible, for example, that all this energy is produced in in a small number of particles at much higher energy, or in a large number of particles at much lower energy. Whereas for BBN, if you're making a lot of photons, for example, MeV photons are pretty effective at disrupting BBN. A factor of a billion smaller number of TeV photons, maybe not so effective. Okay, so there are subtleties here. This is just counting up total power injected, but it's enough to see that there is a potential signal that you need to look for. I see some questions.
But here we assume that the cross-section do not scale with temperature, right?
Good. Yes. Right. So there are. You're preempting me a little bit, but that's fine. So yeah, so I've made an assumption here that sigma v is just a constant, that it's not a function of any other parameters in the problem. That is often true, but not always true. And if you just take the expressions that you learned in QFT for how the cross-section relates to the matrix element, and you work out the cross-section for non-relativistic particles with a matrix element that has no momentum dependence in the non-relativistic limit, then you will generally find that sigma scales as 1 over v. And sigma v is approximately constant. But there are exceptions to this. If there's a momentum dependence in your matrix element, then you can have, for example, p-wave suppressed cross-sections. So in that case, sigma v would drop as a function of v precipitously. We would get extra factors of a in here coming from the momentum scaling, and that would kill this BBN constraint. And it will kill the next couple of constraints I'm going to be talking about as well. You can have the opposite case, well, a somewhat opposite case as well, where if you have long-range interactions between dark matter particles, then you can largely ignore those long-range interactions when the kinetic energy of the dark matter particle is much higher than the potential energy. Once the kinetic energy drops low enough, the attractive potential becomes important, and that can enhance the dark matter annihilation rate a lot. So then you get extra factors here that go the other way, and the BBN constraints become pretty strong, but constraints from later times and lower velocities become even stronger. So yeah, what I'm showing you here is the simplest case, where it's just the simple tree-level annihilation, no momentum dependence. But if you have velocity dependences in either direction, it can alter these constraints by a large amount. This is generically true of indirect detection bounds. Or there may be a dependence which isn't velocity dependence. For example, if you're looking at asymmetric dark matter, all the anti-dark matter has annihilated away in the early universe. Then you're not going to get it. You're not going to get a signal like this. So yeah, I'm doing the simplest case here, but yeah. So this tells you that it's worth looking at these constraints and exploring them in more depth. But there are certainly models that can evade them, and models that are more constrained. Were there any other questions? Yeah, I saw one back there. Sure. So we've argued that in the radiation-dominated epoch, and BBN is still within the radiation-dominated epoch, then this rate should scale like 1 over A. Okay? Now, if we ignore, which I'm doing for the moment, if we ignore changes in G star, so we ignore changes in the relativistic degrees of freedom, then 1 over A just scales like the temperature of the universe. Okay? So this is saying that this rate just scales like the temperature, and we know that this rate was order 1 at freeze out. Like, that's what freeze out means. That an order 1 fraction of dark matter is annihilating in a Hubble time. The point. So if I know that freeze out was at 5 GeV, and BBN is at 1 MeV, there's a difference of 5,000 in temperature between those two scales. Okay? So that's where the 1 in 5,000 comes from. Make sense? This is the quickest way I know to just get simple estimates. I mean, of course, you can also go through and calculate properly what is the density of dark matter at the BBN epoch. Just put in n squared sigma v. But, and that will give you something close to the same answer. But if you take G star into account properly, you will get slightly different answers. But okay. Oh, good. Yeah, okay, good point. So yeah, so I have picked a number. No, good point. Yeah, so for the specific numbers that I've picked, for this, well, I mean, it's still, because the energy density scales like G star T to the 4th, the change in scaling of T with A is like G star to the 1/4 scaling. So even though G star is changing by a pretty big factor, the change in the temperature from this, yeah, don't take this any more seriously than an order of magnitude estimate, okay? I mean, if you want to do it more carefully than an order of magnitude estimate, you need to do more work. But at an order of magnitude level, it's usually fairly safe to ignore G star. Okay, so that's the first thing. Dark matter annihilation injects enough energy that it can potentially perturb BBN, and from changes in the helium abundance and in the abundance of the subdominant elements, such as lithium and deuterium, you can actually set fairly interesting constraints on thermal dark matter annihilation. Let's go down to the next epoch where we have a strong observational constraint. So the CMB, as Neil said yesterday, it happens at about 0.2 eV, but I'm going to just say that this is approximately 1 eV. As I said, these are all order of magnitude estimates. So this is fairly shortly after matter radiation equality. If I put it properly at 0.2 eV, it would have a small amount of evolution after matter radiation equality as well. But if we take this number, okay, so this is 1 eV. Let's say we've essentially been in the radiation-dominated regime for all the time from freeze-out until this point, since this is pretty soon after matter radiation equality. So this is, so from 5 GeV to 1 eV is 5 times 10 to the minus, is a factor of 5 times 10 to the 9. So this tells me that order that a fraction of like roughly 1 in 5 billion dark matter particles will annihilate per Hubble. So, again, we can ask the same question. How much power does this correspond to? Well, this is roughly 1 in 5 billion of the dark matter energy density that's potentially being converted into visible channels through annihilation. So that corresponds to about 1 in a billion of the baryon energy. Okay, so that means that we're producing on average about an EV of energy per hydrogen atom, or 10 EV of energy for 1 in every 10 hydrogen atoms. What's the ionization energy of hydrogen? Yeah, 13.6 EV, which is 10 EV at the order that I'm working. So what this tells us is that this is enough energy to ionize 10% of the hydrogen in the universe. Okay, so this is a recombination. So at the recombination epoch, the universe goes from being almost completely ionized to almost completely neutral. If after recombination, when the universe was almost completely neutral, we had some process that kept the universe 10% ionized, it would be very noticeable. The CMB experiments at present set limits. So the experiments that measure the CMB anisotropies are at present sensitive to changes at the level of a few times 10 to the minus 4 in the ionization fraction after recombination. So if a few extra hydrogen atoms per every 10,000 are ionized, we would know from the CMB experiments. Okay, so when you do this calculation in detail, the effect is not quite this strong. The effect is that once you take into account properly the entropy dumps, the change in G star, you take into account the fact that not 100% of this energy that is produced goes straight into ionizing hydrogen. There are other channels that it can go into as well. It can heat the gas, it can excite the gas, and just can distort the CMB. It can end up in high energy free streaming gamma ray backgrounds. Once you take all this into account, I mean, from this it looks like I could just rule out 100 GeV thermorelic dark matter instantly, right? And by a couple of orders of magnitude. So it's not that good. But it turns out that when you do this carefully, and I'll talk more about this over the next couple of days, you can pretty much rule out thermorelic dark matter below a few tens of GeV if it annihilates into anything that is not neutrinos. So any standard model channel that isn't just neutrinos. Again, caveats to this are if it's suppressed at low velocities, if it's asymmetric, so there's no anti-dark matter left, then that will again kill this signal. But the simplest S-wave dark matter annihilation models at low masses are actually quite constrained by these bound-stream cosmology. Yeah.
So even if you annihilate to neutrino, you will still have bound from ineffective.
That's right. Yeah. So I was actually going to talk about that next, but. So yeah, so I'll go ahead and talk about this now. Yeah, so these bounds that I'm looking at here are from energy injection, and for these two particular channels, BBN and CMB, the most dramatic effects that these energy injection can cause is if they inject electromagnetically interacting particles. So then they can interfere with all the other electromagnetically interacting stuff going on in these epochs. But you might say, okay, let's suppose I go 100% into neutrinos, or 100% into some dark radiation that is invisible and just redshifts away, or something like that. Then there is another kind of CMB constraint, which is the constraint from the number of effective degrees of freedom. So the other CMB bound is limits on n effective. So I think you talked about the number of effective degrees of freedom last week. Is that correct? Is it not correct? So, sort of? Okay. I wasn't here last week, so relying on you guys to tell me what you did and did not cover. But okay, so the number of effective degrees of freedom is, effective relativistic degrees of freedom is just what it sounds like. The number of species of relativistic particles that you have around, weighted by the number of degrees of freedom that each of them carry. So the way that it's traditionally defined is that if we look at the total energy density in radiation, then that's the total energy density in photons, which we know about, plus 3 times the energy density in each neutrino species, plus 3 times the energy density in a neutrino species times, plus the energy density in a neutrino species times the number of effective extra neutrinos. So another way that we can, so I'll call this delta NV, so we can write this N effective. So this is the definition of N effective. The reason for these extra factors here, 7/8 is just because, so this is, the reason this expression is written this way is the number density of a neutrino species is somewhat lower, or the energy density of a neutrino species is somewhat lower than the energy density of the photons for 2 reasons. One is that neutrinos are fermions, not bosons. That gives you this factor of 7/8 here, rather than 1. The other reason is that the temperature of the neutrinos is somewhat lower than the temperature of the photons. And if you assume that the neutrinos decouple and then subsequently the electrons and positrons freeze out, and that decoupling happens instantaneously, then you find that the temperature of the neutrinos and photons differs by this factor, 11/4 to the 1/3. So because energy density scales like the 4th power of the temperature, the energy density in the neutrinos would scale like 11/4 to the 4/3. So N effective here is counting the number of extra degrees of freedom that behave exactly like neutrinos. Okay? But all we really care about for this constraint is the total energy density in radiation. So these additional contributions, they could come in the form of extra Majorana fermion species, or extra scalars, or extra light, or extra gauge boson, like gauge bosons, or something along these lines. So N effective here is the effective number of neutrino species. N effective in the standard model, so you might think, okay, in the standard model N effective is 3. It's actually slightly higher than 3 because some of the approximations I made are not completely right. Like the electrons are starting to become, electrons and positrons are starting to become non-relativistic when the neutrinos decouple from the standard model. That decoupling isn't instantaneous. So just the ordinary neutrino species give you a slight contribution to N effective away from 3. So the observations here, so from BBN, you can say basically that delta N effective, by which I mean N effective minus 3, is less than about 1. You can accommodate maybe 1 more degree of freedom that looks like a neutrino. From the CMB, the current constraints on N effective are that Planck in 2013 found that N effective was about 3.15 plus or minus 0.23. This is a 1 sigma error bar, but still, it's pretty hard to accommodate even 1 extra neutrino-like degree of freedom. So how is this relevant to dark matter? Well, this is relevant to dark matter in a couple of possible ways. So one possibility is just that if the dark matter is itself pretty light, so the dark matter itself was relativistic during BBN, so not like these 100 GeV particles we've been talking about, but say a 1 MeV dark matter particle, then the dark matter itself could contribute to this n-effective bound. Similarly, if the dark matter annihilates into some dark radiation field, something like that, so that's an extra radiation degree of freedom, that will be constrained by these NF bounds as well. Now, there's a pretty big caveat here, which is that the contribution to the radiation density goes like the temperature of this field to the fourth. So if your dark radiation or dark matter is much colder than the standard model thermal bath, e.g. because it's never been coupled to it, or it was only coupled to it well before the QCD phase transition, and then a lot of entropy has been dumped in the standard model to heat it up, then in those circumstances you can often evade these constraints. But if that's the case, then you're probably not in this thermal freeze-out scenario anymore. The other way that these constraints can affect the dark matter is if the dark matter annihilates away dominantly into neutrinos or dominantly into photons, then it can change the relative temperature of the photons and neutrinos. And that will also perturb this NF calculation. Like if I make the photons much hotter relative to the neutrinos, then it will look like the neutrinos are cold, and thus the contribution to NF would be below 3. The standard model. If I annihilate and make a lot of extra hot neutrinos and heat up the neutrino sector when it's not coupled to the photon bath, then I will get a contribution greater than 3, even though I have no actual extra degrees of freedom. I've just changed the temperature. That's it. For this 100 GeV thermal relic that we've been talking about, let's think about this. So at the CMB epoch, or I mean we'd say at BBN as well, you're talking about, at BBN you're talking about maybe 1 in 5,000 dark matter particles annihilating and dumping their energy. The universe is very radiation dominated at that point. So there's far more energy in neutrinos and photons than there is in the dark matter. So 1 in 5,000 dark matter particles dumping their energy into the radiation bath is a completely negligible perturbation on the energy density of the radiation field. So for the kinds of models that I've been talking about, the 100 GeV WIMP, this is a negligible effect. But for light dark matter, it can be important. So in fact, this is often why Neil showed a plot where he said the thermal range was about an MeV and up. This is the main constraint that makes it more difficult to have thermal relic dark matter below the MeV scale. It's not impossible. There's a recent paper by Berlin and Blinov which basically says that if your dark matter first couples to the standard model below the MeV scale and then freezes out and annihilates away, then the effects partially cancel each other out, and you can fit light thermal dark matter in between. But you need a fairly special thermal history to do that. I'll just pause for questions. Sorry, that sort of leapt off from a question. But does that answer your original question?
Sorry.
Yep.
Did you say that those Planck constraints can constrain thermal dark matter below about 1 GeV?
Below tens of GeV.
10 to GeV. Okay, there's this strongly interacting dark matter rivalry.
Yep. Yeah, so the way they get away from it is what I mentioned. They have a 3-body annihilation as their dominant process during freeze out. So right, but the process that is the process. Okay, so right, so the calibration here, assume that I'm calibrating to a freeze out cross section. Okay, their freeze out cross section is a 3-body cross section. Their 2-body annihilation rate is much smaller, which is why it's subdominant during freeze out. Right? So the 3-body rate, yeah, so you have 2 cross sections that you need to compare to the CMB bounds, because it's not always true in these, the subdominant 2-body annihilation at freeze out can become really important in the CMB epoch. But yeah, so the 3-body annihilation that's actually controlling their freeze out is negligible at CMB time because you have like an extra power of A cubed in the scaling here, and our difference in A is 9 orders of magnitude here. So the extra factor of A cubed really squashes the signal pretty hard. At this low, yeah, so at this low scale, because the density is so much lower, the 2-to-2 will dominate. And we know that the 2-to-2 was not strong enough to control the freeze out. So the cross section is significantly subthermal. Okay, any other questions? Okay, then let me just continue this picture scaling down. So we've talked about BBN and the CMB. So let's just finish this off by bringing this extrapolation back to the present day. So if we go all the way down to the present day, we argued that this A factor drops by about 9 orders of magnitude down to matter radiation equality. Okay, and then from matter radiation equality to the present day, so at matter radiation equality, the temperature was about 1 eV. Today, the CMB temperature is 2.7 Kelvin. This is a few times 10 to the minus 4 eV. So that means that between today and the matter radiation equality temperature, we've got 4 orders of magnitude in A. During the matter-dominated epoch, I'm leaving out the little dark energy-dominated epoch at the end, but during the matter-dominated epoch, this rate scales like A to the minus 1.5. So from today, so from matter radiation equality to today, this rate drops by another 6 orders of magnitude. So that tells us that we would expect that that out in the space between galaxies, we just have the smooth cosmological dark matter density. We'd expect only about 1 in 10 to the 15 DM particles to be annihilating. To annihilate in a Hubble time. And that is a pretty low rate. That is hard to see. But we know that in the present day, our targets for dark matter searches are not just the intergalactic medium. We can look at objects like Virgo or our galaxy. And so just to check consistency with our previous result, the cosmological DM density today is about 10 to the minus 6 GeV per cubic centimeter. At Earth, we said before, it's about 0.4 GeV per cubic centimeter. So if it's 1 in 10 to the minus 15 dark matter particles out in intergalactic space, for densities comparable to that at Earth, we'd expect the rate of annihilation to be roughly 5 orders of magnitude higher. So we'd guess, again, that about 10 to the minus 10 GM particles annihilate per Hubble time for 100 GeV thermal WIMP, which is similar to the answer that we got before. Just, I mean, as it has to be if I did this correctly, but this is just a consistency check. Okay, so I hope with that I've persuaded you that for thermal dark matter at around the weak scale, there are potentially substantial effects on the evolution of cosmic history at BBN and the CMB, and I've reconfirmed that the fraction of dark matter particles annihilating with a density similar to that of Earth is something that you might plausibly hope to see the products from in indirect detection experiments. Are there any questions about any more questions about this before I go on? Thank you for the good questions so far. Okay. Okay, so that's the general sketch. So essentially all the constraints that I show you when we look at the detailed constraints tomorrow are going to be some variation of either looking at the effects of dark matter on the early universe, the effects of heating or ionization at early times, or changes to ineffective at early times, or they're going to be of this form. We've got objects in our local, we've got clusters or galaxy clusters or dwarf galaxies or similar producing visible particles via dark matter annihilation or decay. What can we say to constrain those, and how do we look for them? So then I want to change tack a little bit and just explain some of the terminology about how we do these sort of direct indirect searches where we really are looking for the annihilation products directly, as opposed to their effects in terms of ionizing the early universe or modifying the nuclear abundances after BBM. Okay, so if we're looking at these, I'm really not doing well with this chalk. Okay, so if we're looking, so by present day indirect searches, I mean the dark matter annihilation has happened reasonably close to the present day, as opposed to when the universe was very young. I also, of course, mean searches that experimentalists are doing today, but that's essentially all the searches that will be interesting to us. So, okay. So now, let's say, okay, let's go back to what we did at the start of the first lecture. I have dark matter annihilating out in a galaxy cluster or in our galaxy. I want to understand what is my predicted signal. So there are a few different ways that you can classify these searches. You can classify them by the object that you're looking at. You can classify them by the channel that you're looking in. So are you looking for photons or neutrinos or something else? You can classify them by are you looking for annihilation or decay. So one pretty important distinction in terms of how you model the signal is the channel one. So in particular, whether these annihilation products travel in straight lines or not. So are the annihilation products that you're looking for photons and neutrinos, or are they charged particles? Now, in most models of dark matter, both of these will be produced. So you can look for the same model through both of these searches, but the way in which you need to look for them is pretty different, because for charged particles you can't tell where they came from. Okay? I mean, in principle you can look for an anisotropy, but as we'll see when I show you real results, the current limits on anisotropy are that even if you had a single source producing the bulk of the high energy electrons and positrons we see spewing out these electrons and positrons not very far away from us in astrophysical terms, the expected level of anisotropy is below 1%, and we can't measure anisotropies that well in cosmic rays. So for charged particles, what you can do is you can look to see if there's a signal, and you can measure the spectrum of the signal. And you need to take into account the propagation effects between what happens to these particles between when they are first produced by dark matter annihilation, and when they reach our telescopes. Photons and neutrinos, by comparison, are much nicer in that we can trace them back to their source, which means that we can use spatial profile as a way to discriminate between dark matter signals and possible astrophysical signals. So if you're dealing with the search for photons and neutrinos, a key question that you have to ask is the slightly more sophisticated version of that calculation that we did at the start of last lecture, which is what does my signal profile look like, both spectrally and spatially. By spectrum here, I mean energy spectrum. How many photons or neutrinos or whatever am I producing at a given energy? Okay. So let's focus first on photons and neutrinos. And their spatial distribution. So the picture here is that the dark matter annihilates. So dark matter comes in. Something happens, we don't know what it is. We'd like to figure out what it is. It produces standard model particles. These could be, for example, these could be gauge bosons. They could be Higgses, they could be quarks. They could be three-body states. Then subsequently, these standard model particles, if they're not absolutely stable, are going to decay into other standard model particles. So, I mean, this could be let's talk a bit more about what kinds of different spectra that you can get later, but pretty generically, but in many of these final states, the way that they decay, if there are any hadronic channels, they will hadronize, they will produce neutral pions and charged pions. When those neutral pions decay, they decay almost 100% to gamma rays. When those charged pions decay, they make neutrinos and electrons and positrons. So the generic behavior of dark matter annihilation is that you get all of the above. This isn't universal. If you've got leptophilic channels where there's not a lot of hadrons produced, then this may not be true. So then we have to be a little bit more careful. But the generic behavior is that you get plenty of photons and neutrinos and also charged particles. So the hope is that by measuring the photons produced in this process, we can reconstruct what this final state was. We can try to reconstruct the mass of the dark matter, and we can try to reconstruct this interaction. So the pieces of information that you have in that are the energy spectrum of the particles and where they come from in the sky. We do not usually, with some exceptions, we do not usually have three-dimensional information as to where the photons came from. The exception is when you've got targets at different redshifts. And so then you can say, okay, the signal appears to be coming from this cluster that is a long way away. That means I know at what time it was emitted. I know what redshift it was emitted. But generally, we only have 2D information. So, okay, so let's suppose I have a telescope of area A. Let's suppose, furthermore, that all of these decays that when the dark matter produces standard model particles and those standard model particles subsequently decay to produce the things that we're actually going to look for, all of those decays are very fast on an astrophysical scale. So I don't need to take into account the lifetime of these decays in figuring out, say, where these photons were produced. They just trace the distribution of the dark matter production. Okay, so let's consider, so I have my telescope of area A down here at Earth, and somewhere out in space I have a box of volume dV, and I want to know what is the contribution to my signal from this box of volume dV. So I'm going to work in spherical coordinates because it's simple. So the distance between me and this box is going to be r, and I'm going to, okay, this will actually be like a, it will not be a square box, it will be a sensible box in spherical coordinates. So the volume of this box will be r squared dr d omega, where omega is the solid angle subtended by the box from my viewpoint. So the annihilation rate in this box, so the number of photons produced in this box is going to be, well, okay, so the total number of photons produced is going to be the number of photons per annihilation or decay. But we'll just do this for annihilation. For decay, it's pretty straightforward. Just replace the rho squareds with rhos. So then so for annihilation, the rate of annihilations we said earlier is going to be a half sigma v times ndm squared times, so if I look at it for time dt, so this is the rate per volume per time. So I'm going to multiply by the time I look at it for and the volume of my box. That's the total number of photons. The total number of photons, like coming out of this box, the total number of photons that I actually see is going to be that multiplied by the area of my telescope over 4 pi r squared. Okay, so we can now put in this v here. This n gamma per annihilation, I'm just going to denote as n gamma, okay, but this means the number of photons that I get per annihilation. So this comes from my particle physics model. This is a quantity that you can extract from Pythia or your favored event generator of choice. Everything else in here is astrophysics. So actually, let's pull this factor of 2 out the front, so we'll make this a over 8 pi. We've got a 1 over r squared, so we have an, so that my ndm squared, all right, this is rho dm squared over the mass of the dark matter squared times sigma v, and then I've got a dt d omega dr. The r squared in this volume element is going to be cancelled by this 1 over r squared in here. Okay, so the fact that the object is further away, but as I go further away, the box subtended by a given solid angle becomes larger. So these two factors cancel each other out. So this is my total observed number of photons over a solid angle d omega in observation time dt. So now what I'm going to want to do is, so this is from a specific box subtending a specific solid angle at a specific radius. So what I'm going to look, so my actual observable quantity is going to be something like the number of observed photons per unit area of my telescope, per time that I observe for, and per solid angle that the observation is in. This is going to be, so I'm going to take out these a, dt, and d omega factors. This is then going to give me psi So So this is going to give me a result like this. So the particle physics is encapsulated in these terms. These terms tell me how many photons do I get per annihilation, what's my overall annihilation rate, and what's the mass of the dark matter. This term, this rho dm squared term, is encapsulating everything about the astrophysics, everything about the distribution of the dark matter. So what rotation curves tell you about, what gravitational lensing tells you about where the dark matter is, all that goes into this piece. So while it's critical to understand the distribution of dark matter, just to understand the properties of dark matter, that's how we've gotten a lot of information of what we do know about dark matter in the present day, it's also a really key input to indirect searches. So the way that this is traditionally, so for decay, everything is very similar, except that there's only one power of rho here, and you should replace this sigma v over mdm squared with 1 over the dark matter mass times the lifetime, and this 8 pi with a 4 pi. So just write that out. Yep.
About this n gamma per annihilation, is the small n, is it a number density or is it
Oh no, yeah. So no, it's the actual number. I can make it. Is capital N more consistent with your previous? Okay, we'll make it.
capital N on the left side is also the
Okay, yeah, that's why I didn't write it as capital N. Okay, I'm going to leave it at lowercase n, but yeah, this is the actual number of photons per annihilation, not the number density. So like
number density or
capital N. Okay, good. Capital N here is the total number of photons that I see. So it's not a number density. It's the total number of photons observed by my detector if my detector has an area A over a given observation time from a given distant volume V. So let's see how that, yeah. So the only thing that's the number density here is this mdm squared. So let's just check the units on this. So sigma V has units of centimeters cubed per second, length cubed per time. Okay. That I'm going to multiply by 2 powers of mdm squared, which has units of say 1 over cubic centimeter. So then this altogether has units of 1 per volume per time. Then I multiply this. So this is all just a dimensionless quantity on this side. I want this a over 4 pi r squared is also dimensionless. So this dn gamma and this n gamma, they're both dimensionless, they're both just counts. Okay? Thank you for asking for clarification, but that's yeah, that's a good thing to have. So for decay, if I want the same answer, I want the number of photons that I see per solid angle, per area, per unit time. It's going to be much the same calculation. Okay, so all that I've done is replace the parameters controlling the annihilation rate with the parameters controlling the decay rate. Tau here is the decay lifetime, and rho is just a single power of the density of dark matter. Okay, so there is a conventional, so there is a deficit. So what we often do is we say, all right, this is your particle physics dependent factor. You come up with whatever dark matter model you like, that will feed into here. But we can describe this astrophysical factor without saying anything about the particle physics. Caveat here is, if sigma v depends on, say, velocity, or sigma v depends on some other parameters, then you can't pull sigma v outside this integral, because the velocity of the dark matter particles is going to depend on where you are in space, in general. So what I've done here is effectively assume that sigma v is just a constant. If I have a velocity dependence, then these j factors will not be correct. You need to recalculate them with the appropriate velocity dependence or dependence on other parameters inside the integral. But the usual picture is that we describe the j factor of an object to be the integral to be 1 over 8 pi times the integral over Okay, so this is just saying if we look over the solid angle that the object subtends on the sky, so this is for an object such as a cluster or a dwarf galaxy. We perform this integral, then we can feed this integral back into this calculation. Now, I should note there is variation in the literature as to whether this factor of 8 pi is there or not. Okay, some people roll it. This is, as far as I can tell, the most common definition, but sometimes this is definitely true. This is invariant, but which piece of this you call the J factor up to constant factors is not the same between all sources. So if you're getting funny J factors, check if they're off by a factor of 4 pi. I know of at least one paper where this mistake led to people setting a factor of 10 worse limit on dark matter than they could have, because somebody thought the J factor didn't have the 4 pi in there and it actually did. So their limit was a factor of 4 pi weaker than it should have been, which wasn't discovered until somebody else tried to do the same analysis several years later and realized that they could have set a much more competitive limit if they had noticed this factor. So, okay, so this is just a definition. So what are the typical sizes? So for annihilation then, assuming that sigma v is just a constant, then apart from that model dependence, you can immediately just say, no, okay, what's the best target for my annihilation signal? You can ask, how do J factors compare between common objects? So if you look at regions, so I'll first tell you what some numbers are, and then I'll tell you the assumptions that go into them. So there are some non-trivial assumptions. So if you try to estimate, for example, what is the J factor of the dwarf galaxies of the Milky Way? So the dwarf satellite galaxies of the Milky Way are highly dark matter dominated systems. They orbit around our galactic halo. It's thought that they were formed earlier in the universe and then picked up. So they're small, they're cold, the velocity dispersion in them is low, and they can be quite dense. They're nice for a couple of reasons in indirect detection searches. One is that compared to clusters and so on, they're relatively close. I mean, we talked about Virgo being, order 15 megaparsecs away. The closest dwarf galaxies are more like tens of kiloparsecs away. So that 1 over r squared factor is much less of a problem. So dwarf galaxies are relatively close. They have a high dark matter content. And most importantly, they have very few baryons. So they're low background systems. So the backgrounds are fairly minimal. The J factors that you get for these dwarf galaxies for annihilation are somewhere in the order. So the absolute value of this number won't mean very much to you. I'm just going to compare it to another region, and then you'll see how much stronger it is. Okay, so in these units, they're like 10 to the 17, 10 to the 20 GeV squared per centimeter to the 5. The Galactic Centre is another region that people look at a lot. It's very close to us. It's only 8.5 kiloparsecs away. It is probably the biggest concentration of dark matter anywhere in our galaxy, just because dark matter falls into the center of the gravitational potential. The danger of the Galactic Centre is that for orbit a few signals, the backgrounds can also be very large. The Galactic Centre is a great place to look for gamma ray lions, like spectral lions, and other signals where the astrophysical backgrounds are rather low. It's a difficult place to look for a signal that can be mistaken for astrophysics, and I will give you a couple of examples of that from my personal experience. But the reason why it'd be a great place to look for dark matter is that if we work out the J factor for the Galactic Centre, so again, I have to specify, by this definition of the J factor, I have to specify an angular region to integrate over. For just the 1 degree surrounding the galactic center, the J factor is about 10 to the 22 GeV squared minus 5. I'll explain to you the assumptions that go into this, but within these assumptions, what you're seeing is that if you were to see a 3 sigma signal in the dwarfs, you know, maybe there are 10 or 20 photons in the dwarfs faint signal, the signal that you expect to see in the galactic center is about 100 times as large. So the galactic center is a place to go hunt for high statistics. Now, sorry?
What are the typical uncertainties in this J factor?
Huge. That's what I'm about to get to next. Yeah, so the uncertainties in these J factors can be pretty large, but the type of uncertainty differs. So for the dwarf galaxies, for example, the challenge in ascertaining the J factors is mostly to do with these dwarf galaxies. They have very few stars associated with them. Again, the way that you work out the dark matter density and the dark matter profile is similar to the old rotation curve studies by Rubin et al. Back in the 1970s. You look at these stars, which you believe are bound to the dwarf galaxy. You look at their velocities, and you try to infer from that how much dark matter is contained within the system. The problem is that if you've only got, say, for the ultra faint dwarfs, which are the most dark matter dense, the coldest and maybe the best targets for low background, the number of stars associated with the system may be order 10. So it's hard. There are large uncertainties. There are significant uncertainties just in terms of how do you model the profile. You can get nominally rather small uncertainties if you don't give the profile very much freedom, but that may be misleading. Like if you give the density profile of the dwarf a lot more freedom, you can find that there's actually a much larger range of possibilities. So for the dwarfs, these J factors uncertainties are typically about 1 order of magnitude. They can be higher if it's not clear which stars are actually bound to the dwarf. Like, I mean, it's possible to have calculations where you do a calculation of the dwarf J factor, you do another calculation leaving out 1 star that you thought was bound to the dwarf, and the answer changes by an order of magnitude. This can happen for these ultrafaints. So typically about 1 order of magnitude uncertainty. This became a big issue a couple of years ago. Well, I mean, there are still very tentative hints of maybe 2 sigma gamma ray excesses coming from a couple of these dwarfs. Whether you think they can possibly be a dark matter signal or not, the picture would suddenly be much clearer if we had uncertainties of less than an order of magnitude on the J factors, because you don't see them from other dwarfs. So then the question is, well, are these 2 dwarfs, do they genuinely have that much more dark matter than the other dwarfs that you would expect to see signals there and not anywhere else? It's a difficult problem. So for the galactic center, the situation is somewhat different. So these J factors are derived assuming what's called a Navarro-Frank-White density profile. So Navarro-Frank-White density profile says that the dark matter density scales like this. So RS here is some scale radius, which for the Milky Way is about 20 kiloparsecs. So this profile says that the dark matter density scales roughly like 1 over r at small distances and like 1 over r cubed at large distances beyond the scale radius. Now, so this is based on simulations. So you can also look up the Inasto profile, which is another profile derived from simulations. It's broadly similar to this, steeper slope at large r, flattens off at smaller r. It flattens off a bit more. But in both cases, you have a large rise in the dark matter density at scales, at radii smaller than the scale radius. So this kind of behavior where rho of r continues to rise steeply at small r is called a cusp, density cusp. Okay. Now, so the presence of this cusp is pretty important to this high J factor, since here we're looking at a radius only 1 degree around the galactic center. So I said the scale radius here is 20 kiloparsecs. 1 degree on the sky is about 150 parsecs from the galactic center. So this whole region in here is well inside the scale radius and is benefiting from this R over RS factor, from this RS over R factor, which then gets squared. Okay, so the uncertainties in the galactic center J factor come from uncertainties in how the density distribution rises at small r. Sorry. Because as I discussed earlier, it's very hard to actually dynamically measure the density of dark matter close into the galactic center just because the baryons dominate the potential there. So you can measure the total enclosed mass. That tells you how much ordinary matter there is, not how much dark matter there is.
So, while according to J factor, do you consider the possibility that there are ionized medium between you and the source?
Okay, yeah, so that's a good question too. So, right, I was going, so the J factor result that I wrote down here is somewhat incomplete in two ways. One is that, yes, the photons that you see may be absorbed on the way to you. If you're looking at gamma rays, this isn't much of an issue for regions within our galaxy. Our galaxy is particularly optically thin to gamma rays, likewise for neutrinos. But if you're looking at lower energy photons, then yeah, you need to put an absorption term into this integral. The other thing that you can add into this integral, which I will talk about after I talk about these uncertainties, which may be tomorrow or Thursday, is that if your objects are sufficiently far away, you also need to put a redshifting factor into this J factor calculation. The result that in the case where the redshift is negligible, the spectrum at the source, and then absorption is negligible, the spectrum at the source is basically the same as the spectrum that we see. And so it really is only the J factor that you care about that depends on distance. But if you're accounting for contributions from high redshift as well, obviously the photons from that will have been redshifted by the time they get to you, and that will distort the spectrum, not just change the amplitude. Same for absorption. If you absorb preferentially low energy photons or high energy photons, it can distort the spectrum too. So this question of how the density really behaves at small r, this is based on n-body simulations which only contain collisionless cold dark matter and have no baryons in them. There is some evidence, mostly from dwarf galaxy-sized halos, that these cuspy profiles might fail observationally at small radii. So there are some observational hints that real galaxies have what I would say is chord profiles, by which we just say the density does not rise so sharply toward the origin. So the hypotheses often suggested for this are this could just be due to baryonic feedback. It's just a statement. If there are large outflows of baryonic matter from the center of the halo, this effectively shakes up the gravitational potential. If you've got a dark matter density cusp, in that potential, then perturbing the potential can cause it to flatten out. The other possibility that's often suggested for this is maybe dark matter self-interactions could flatten out the core. But as I said earlier, in the Milky Way, we don't really have any observational evidence as to what the density profile is doing at its center as yet. And where the baryonic feedback matters for galaxies this size, you get very different core sizes in different simulations that make different assumptions about how the baryonic matter is behaving. So this is, I would say, a fairly optimistic J factor for the Galactic Centre. It's probably worth doing searches there in case you see something, but it is fairly consistent with our current constraints if the dark matter density essentially flattened out at radii not much smaller than the distance of the Sun from the Galactic Centre. So this is not an uncertainty. So the uncertainty on this is not associated with modeling with any observations. It's uncertainty in the halo model. Okay. So given the time, if you're wanting coffee, I'll just say one more thing before we wrap up for the day, and then tomorrow we will talk, we'll do one last point on J factors, and then we will talk a bit about cosmic rays. So, okay, so there are two more points I want to make about J factors. One is substructure in halos can be important, and also a large source of uncertainty. In cold dark matter scenarios, small halos form first. They accrete together to form large halos. This means that in a galaxy size or galaxy cluster size halo, we expect there to be many small dark matter clumps strewn throughout the halo. If the density in those clumps is high, the annihilation rate in those clumps can be high. And that's not included in that NFW profile that I just erased. So that can potentially increase the annihilation rate significantly, but the smallest clumps are very hard to simulate because they're small and there are a lot of them. So this is not well understood either observationally or from simulations. So these are places where there's ongoing work to do a better job of understanding these substructures, as well as to do a better job of understanding these dwarf galaxies and density profiles, both for their own sake and because they're a pretty key ingredient for indirect detection. Okay, now that's true for annihilation. Decay is free from this uncertainty because it only cares about the total amount of dark matter in a structure, not how it's clumped. Okay. Okay. So I will call it there. At the very start of next lecture, I'll just fill in your question and just write down explicitly how to include effects of redshifting on the spectrum, just because it's a little non-trivial to get all the factors of 1 plus z right. It's just so that you have it there as a reference and see how to do it. Then we'll talk about the more difficult case of cosmic rays. Well, it's more difficult in a way in that they propagate in galactic magnetic fields, but you don't really have spatial information available. You can just look at the spectrum. And then I'll show you the applications of these, that if you take these constraints, if you take everything that we've talked about for the last couple of lectures, then what do you actually get in terms of constraints on dark matter models? Okay, enjoy your coffee. See you tomorrow.